Neptune has always looked quiet from a distance, a cold blue world, far beyond Saturn, drifting in darkness under a faint sun. But now NASA has found something on Neptune that scientists have been trying to confirm for decades. For the first time, strange auroral light has been directly detected there, and it is not appearing where many would expect. Tonight, this journey moves from the dark space around Neptune into its upper atmosphere and deeper hidden layers to see what this new discovery really means. If this kind of deep space documentary is enjoyable, please like the video, subscribe to the channel, and stay for the full journey. Far from the Sun, where daylight on Neptune falls to something like a long dim twilight, the story begins not on the planet itself, but in the dark space around it. Neptune travels more than 30 times farther from the Sun than Earth does, and at that range the familiar force of sunlight has thinned into a pale and weakened presence. The warm brilliance known near Earth no longer fills the sky with strength. Even at local noon above Neptune, the Sun would appear small and intense, but its light would be vastly fainter than the light received by Earth. This great distance matters because any new discovery at Neptune must first be understood in terms of the environment that reaches the planet from outside. What arrives there from the Sun does not arrive quickly in any human sense, and it does not arrive with the same power it carries in the inner solar system, yet it still arrives. The Sun continues to send a flow of charged particles outward across the planetary system. NASA describes this flow as the solar wind, a continual stream moving outward through space and bathing everything in its path, all the way toward the edge of interstellar space. Neptune remains inside that outward stream, though only at its far and weakened margin. The solar wind is not wind in the earthly sense. It is not moving air, and it does not rustle, press, or cool in the ordinary way. It is a flow of charged particles, mainly electrons and protons, released from the Sun's outer atmosphere and carried through the solar system along with the Sun's magnetic influence. A charged particle is simply a particle with electric charge, which means magnetic fields can redirect its motion. This detail is quiet, but it governs much of what later becomes visible around magnetized worlds. The important outer condition is simple. Neptune does not drift in empty stillness. It sits inside a very thin but active stream of solar material that crosses billions of kilometers before reaching the planet. By the time that stream arrives so far from its source, it has spread widely through space. Its density is low. Its effects are difficult to see with ordinary eyes. But in planetary physics, even sparse matter can matter greatly when it carries energy and charge across such enormous distances. Auroras, on Earth and elsewhere, form when energetic particles interact with a planet's magnetic field and upper atmosphere. The newly announced detection of auroras at Neptune by NASA's James Webb Space Telescope therefore begins at the outermost level, with the arrival of solar particles from very far away. This outer region is quiet in appearance. There are no broad clouds, no bright rings of colour hung in visible emptiness, and no obvious walls marking where the Sun's influence ends and Neptune's begins. Space around the planet remains dark, cold, and almost entirely transparent. Yet it is not inactive. The solar wind flows through it. Magnetic pressure, particle energy, and the slow changing state of the Sun all continue to shape conditions there. Neptune receives no intense or constant particle bombardment in the dramatic language often imagined in popular art. Rather, it endures a subtle and distant space weather, a changing external state produced by the Sun and carried outward over time. Space weather means the variable conditions in space caused by the Sun. especially changing flows of particles and magnetic activity. At Neptune's distance, this weather is remote and faint compared with the conditions nearer the Sun, but it still establishes the external setting in which the planet's magnetic environment must operate. The remoteness of Neptune gives this setting its special character. Near Earth, auroras are familiar enough to belong to ordinary human experience in some places and seasons. At Neptune, the same broad physical principle must work across a much deeper spatial separation. Solar activity still matters, but the connection is stretched across the vast width of the solar system. This is part of what makes the new detection so scientifically important. Neptune has long been expected to possess auroras because Voyager 2 detected clues consistent with magnetic and atmospheric conditions that should allow them, and because other giant planets in the solar system show auroral activity. Yet direct confirmation remains difficult. The planet is distant, faint, and cold. Its upper atmosphere has to be observed under weak sunlight from across billions of kilometers, and the signature of auroral activity has to be distinguished from the planet's own dim infrared glow. The recent Webb result finally provides that direct evidence, but the outer region itself remains the beginning of the explanation, a distant world receiving a distant solar wind, still linked physically to the Sun despite the long reach of space. What the outer environment shows most clearly is continuity. The solar system does not break into separate isolated chambers as distance increases. The Sun's influence weakens with distance, but it does not suddenly vanish after Jupiter or Saturn. It continues outward past Uranus and onto Neptune. The charged particles become sparser, the light becomes weaker, and the timescales of change become longer, but the physical relationship remains. Neptune is still part of one connected heliophysical system, meaning one large sun-shaped environment of particles, fields, and radiation extending across planetary space. Because of this, what NASA now finds at Neptune is not merely a local curiosity. It is evidence that even the most distant major planet remains dynamically tied to the star at the center of the system. The tie is faint, delayed, and transformed by distance, but it is real. In that dark outer setting, the silence of the scene becomes part of the science. Neptune orbits where sunlight is weak and where the solar wind arrives only after a long outward crossing. The space around the planet seems nearly empty, yet it carries the ingredients needed for subtle planetary light. The newly detected auroras do not begin as bright curtains already hanging over Neptune. They begin here, in the slow arrival of solar particles from a distant sun, in the persistence of outward magnetic influence, and in the quiet fact that even at the far edge of the planetary system, the Sun still reaches outward and touches what circles there. Around Neptune, the first great local structure is not a cloud deck, a ring system, or a visible shell of gas. It is the magnetosphere, an invisible magnetic domain formed where the planet's internal magnetic field meets the solar wind. A magnetosphere is a region around a planet in which the motion of charged particles is strongly shaped by that planet's magnetic field. At Neptune, this region is large, dark, and physically active even though it cannot be seen directly in ordinary light. It exists because Neptune is not only a world moving through the outer solar system, it is also a magnetized world, carrying its own field into surrounding space. NASA describes magnetospheres as magnetic bubbles created around planets, and Neptune has one of its own, measured in detail during the Voyager 2 flyby and now understood as a major part of the planet's outer environment. The outer magnetosphere is where the incoming solar wind first has to respond to Neptune rather than continue across space unchanged. The solar wind arrives from the direction of the Sun, carrying charged particles and the Sun's magnetic influence across the vast distance to Neptune. When that flow meets the planet's magnetic domain, the meeting does not resemble a collision between solid objects. There is no sharp wall of matter. Instead, there is a gradual electromagnetic contest in which moving charged particles encounter a planetary field strong enough to redirect them. The result is a boundary in a surrounding region in which the solar wind is slowed, deflected, and partly organized around Neptune's presence. This is why the magnetosphere matters so much. It is the place where the empty-looking space around Neptune stops being only solar space and becomes Neptune's own external environment. Its broad shape follows a familiar planetary pattern, though Neptune gives that pattern its own distant version. On the side facing the Sun, the magnetosphere is compressed by the incoming solar wind. On the side turned away from the Sun, it stretches outward into a long tail called the magnetotail. NASA's visual and descriptive material on the outer planets states this. Simply the Sun-facing side meets the solar wind, and the tail points in the opposite direction. This long night-side extension means Neptune's magnetic environment is not a neat sphere centered evenly around the planet. It is a shaped domain, pressed on one side and drawn out on the other. Even in the deep outer solar system, where the solar wind is weaker than it is near Earth, it still has enough influence to give Neptune's magnetic bubble an oriented form. The outer magnetosphere is not just shape, it is motion. Charged particles entering or approaching this region do not move as they would through empty space. Magnetic fields curve their paths, trap some of them temporarily, and guide them into organized populations and flows. Because the magnetic environment is large and dynamic, the region around Neptune becomes a place of circulation rather than simple passage. Particles can gather in certain regions, move along field-guided paths, and interact with changing magnetic conditions as the planet rotates. The space around Neptune therefore behaves less like a blank volume and more like a physical system. It remains extremely tenuous by ordinary standards, but it has order. Voyager 2's measurements give scientists some of the first detailed evidence for the strength, extent, and diversity of the outer planet's magnetospheres, and Neptune becomes part of that wider picture through direct spacecraft observation, rather than inference alone. Distance from the Sun gives Neptune's magnetosphere a particular calm severity. Near Earth, the solar wind and planetary magnetic response can be discussed in relation to storms, satellites, and human technology. At Neptune, the same fundamental physics takes place in a much colder and more remote setting. The Sun is small in the Neptunian sky. The solar wind is thinner. Communication with spacecraft takes many hours, yet the magnetic response remains real. This is important because it shows that planetary magnetism does not belong only to the active inner solar system. Neptune, though far away and dimly lit, still sustains an extensive magnetic environment capable of intercepting solar particles and organizing the space around it. That persistence is part of why the recent direct detection of auroral activity is scientifically meaningful. It confirms that the distant magnetic system is not merely theoretical or historical, but presently active. The outer magnetosphere also changes how one imagines Neptune itself. Without it, Neptune might appear simply as a blue planet with weather, rings, and moons moving through the dark. With it, the planet becomes the center of an invisible domain that extends far beyond the visible disk. The true outer extent of Neptune's immediate influence is therefore larger than the planet's atmosphere or cloud tops suggest. A spacecraft approaching from afar would not first enter cloud, ring, or moon territory in the physical sense. It would first enter the larger electromagnetic environment associated with the planet. This is one reason magnetospheres matter in planetary science. They make a planet bigger than it looks, not by adding visible bulk, but by adding a surrounding region of structured interaction with the Sun. What Voyager 2 helps reveal is that this environment is not generic. NASA's summaries of Neptune's magnetosphere emphasized that the planet's rotation axis is already notably tilted, and that its magnetic axis has a large tilt relative to that rotation axis, even without yet dwelling on the exact implications of that unusual geometry. The outer magnetosphere can already be understood as variable and somewhat misaligned in comparison with simpler cases. It is not a perfectly centered, steady, and symmetrical shell. It is shaped by the direction of the Sun, by the planet's rotation, and by the underlying orientation of the magnetic field itself. This gives Neptune's outer magnetic region a changing character as the world turns and as solar conditions vary. It is not chaotic, but it is complex. The recent Webb result gives the outer magnetosphere a fresh importance, because it reconnects this invisible region with observable light. NASA's report on the discovery explains that auroras occur when energetic particles, often originating from the Sun, become trapped in a planet's magnetic field and eventually strike the upper atmosphere. Before they can do any of that, they must first encounter the magnetic environment that captures and redirects them. This outer region is therefore the first local stage in the newly confirmed chain of events. The auroral glow itself belongs elsewhere, but the magnetic preparation begins here, in the large surrounding bubble where Neptune meets the solar wind. The discovery does not make the magnetosphere newly real. It makes its present activity newly visible through the consequences of its work. In the outer magnetosphere, Neptune reveals itself as more than a remote blue world. It is a planet that occupies and shapes a volume of space far larger than its visible body. The Sun still reaches it, but not directly and not simply. Between solar particles and the planet lies this invisible magnetic domain, compressed toward the Sun, trailed into darkness away from it, and active enough to hold, redirect, and organize matter that would otherwise continue across the outer solar system. The magnetosphere is therefore Neptune's first great local boundary, not a wall, but a region of control. In the cold and dark around the planet, that control is the quiet beginning of what NASA has now been able to detect. What makes Neptune's magnetic environment truly unusual is not merely that the planet has a magnetosphere, but that the field shaping that magnetosphere is strongly misaligned with the planet itself. Voyager 2 discovers that Neptune's magnetic field is tilted by about 47 degrees from the planet's rotation axis, and NASA also notes that the field is significantly offset from the planet's physical center by at least a little more than half a planetary radius, or about 13,500 kilometers. These are not small adjustments in geometry. They mean that the magnetic system of Neptune is not arranged like a neat invisible bar magnet placed squarely inside the planet. It is a magnetic field that leans and sits off-center, so the surrounding space is organized in a way that is more complex, more variable, and less symmetrical than many older planetary pictures might suggest. A rotation axis is the line around which a planet spins. On Neptune, that line already has a substantial tilt relative to the plane of its orbit around the Sun. The magnetic axis is a different line, the one that describes the overall orientation of the planet's magnetic field. At Earth, these two are not identical, but they are close enough that the broad magnetic pattern remains familiar. Auroral activity is concentrated toward high latitudes and the magnetic field behaves, in first approximation, like a centered dipole. A dipole is the simplest magnetic pattern, with one broad north magnetic region and one broad south magnetic region. Neptune does not follow that quiet pattern. NASA's descriptions emphasize that. Like Uranus, Neptune has a magnetic axis with a large tilt relative to the rotation axis, and that this geometry gives the planet a more variable magnetosphere than the better aligned cases of Earth, Jupiter and Saturn. The offset of the field from the planet's center matters just as much as the tilt. If a magnetic field were strongly tilted but still centered, its surrounding geometry would already be unusual. But when the field is also displaced from the center of the planet, one side of the magnetic system can lie closer to the atmosphere than another, and the external field lines can gather and stretch in uneven ways as the planet turns. NASA's Voyager summaries state that Neptune's field is offset by at least 0.55 planetary radii from the physical center. In simple terms, the invisible magnetic structure is not seated neatly inside the visible globe. This helps explain why Neptune's magnetosphere is described as unusually complex, and why scientists consider its field unlike the more centrally organized magnetic patterns of several other major planets. Because Neptune rotates, this leaning and displaced field does not stay still with respect to the incoming solar wind. As the planet turns, different parts of the magnetic system present themselves toward the Sun and then away from it. The result is a magnetosphere that changes its external orientation through time in a more pronounced way than a more centered and aligned magnetic field would. NASA's scientific visualization material for Neptune emphasizes exactly this point. The combined tilts produce a more variable magnetosphere and suggest a field generation process different from the deeper, more axis-centered dynamos usually invoked for Earth, Jupiter, and Saturn. A dynamo is the process by which motion inside electrically conducting fluid generates a magnetic field. For Neptune, the observed geometry has long supported the idea that the field may arise in a shallower shell of conducting material, rather than in a deep central metallic region. The magnetic field does not simply surround Neptune, it swings through space in a distinctly off-balance way as the world rotates beneath it. This unusual orientation changes where magnetic field lines meet the upper atmosphere. In better aligned planetary fields, the strongest convergence tends to occur nearer the rotational poles. NASA's report on the new Webb discovery states that Neptune's direct auroral signatures appear far from the rotational poles because of the planet's strangely tilted magnetic field, first discovered by Voyager 2 in 1989. The important point in the present outer to inner path is not yet the glow itself, but the geometry that makes such a placement natural for Neptune, even if it appears surprising at first glance. The planet's magnetic poles are not simply close companions of its geographic poles. Magnetic pathways can reach the atmosphere at latitudes that do not match the simple picture formed from Earth. Neptune therefore teaches a careful lesson in planetary comparison. A magnetic field may exist at several worlds, yet the detailed arrangement of that field can alter the visible consequences profoundly. Voyager 2's encounter remains foundational here because it transforms Neptune's field from a remote expectation into a measured reality. NASA's historical summaries continue to repeat this result because it's one of the most consequential findings of the mission. Neptune and Uranus both show strongly tilted offset magnetic fields, and that shared pattern suggests that ice giants may generate magnetism in ways that differ from the larger gas giants and from Earth. Observations indicate the broad conclusion is secure, while the exact internal details remain uncertain. The field has been mapped well enough to establish its unusual structure, but the precise depth, composition, and fluid behavior responsible for that structure are still active subjects of research. The geometry is measured, the full interior cause is not yet finally settled. Seen from the outside, Neptune might first appear as a smooth blue planet in dim sunlight, serene and distant. The magnetic truth around it is less simple. Its invisible field is not upright, not centered, and not static in the easy sense. It leans, it is displaced, and it turns through the solar wind with a changing presentation. That quiet asymmetry is one of the keys to understanding why Neptune behaves differently from more familiar planetary cases. In the dark space around the planet, where charged particles follow field-guided paths rather than straight lines, geometry becomes destiny. The discovery now drawing attention to Neptune begins at this level, not with colour or light, but with an old Voyager result that remains one of the planet's defining traits, an oddly tilted magnetic field, offset from the centre, shaping everything that follows in the upper sky. The first directly seen auroral light at Neptune does not appear where many people would expect it. On Earth, and in the broad popular picture formed from Earth, auroras belong to the high latitudes, gathered toward the north and south polar skies. Neptune does not follow that familiar arrangement. NASA's report on the new James Webb Space Telescope results states that Neptune's auroras are located at the planet's geographic mid-latitudes, rather than being confined to the northern and southern poles. The agency describes the difference in simple comparative terms, noting that the position is more like the latitude of South America on Earth than like the far polar regions. This is one of the most striking parts of the discovery. The newly confirmed light is not merely a distant version of the aurora already known from Earth. It is a planetary light shaped by a different magnetic geography, one that places the visible glow far from the rotational poles of the planet. That location matters because it turns a difficult remote detection into a clear physical statement about Neptune itself. The Webb observations do not simply say that auroras exist there, they show where they appear on the face of the planet. In the published NASA image description, the auroral activity is represented by cyan splotches added from Webb data onto the visible disk of Neptune. Those bright patches do not gather neatly around the top and bottom of the rotating globe. They sit away from the expected polar positions, marking a pattern that is visibly and scientifically unusual. Nature's report of the same observing campaign describes distinct southern infrared auroral emissions, confirming that this is not a vague global brightening but a localized auroral structure. The discovery therefore has shape as well as existence. Neptune's auroras are now known as real and spatially placed phenomena, not merely as an unresolved atmospheric hint. The reason lies in the planet's magnetic field. NASA explains that Neptune's magnetic field is tilted by about 47 degrees from the rotation axis, a geometry first discovered by Voyager 2 in 1989. Auroral activity tends to appear where magnetic field lines converge into the atmosphere, on a planet whose magnetic system is strongly tilted and offset. Those entry regions do not sit where a simple Earth-based intuition would place them. The glow therefore follows the magnetic field rather than the rotational poles. This is the quiet lesson of the mid-latitude auroral zones. The sky over Neptune is not organized by the visible spin axis alone. It is organized by an invisible magnetic framework whose geometry is unusually displaced. What Webb now reveals is the atmospheric imprint of that framework. The light appears where the field guides energetic particles downward, and that location is not the same as the place suggested by the planet's rotational outline. This gives the new discovery a special kind of elegance. For decades, astronomers expect Neptune to possess auroras because the planet has a magnetosphere, and because Voyager 2 provides strong magnetic evidence for a system capable of producing them. Yet expectation is not the same as direct seeing. NASA notes that earlier observations yield hints, but imaging and confirming the auroras prove elusive despite successful detections at Jupiter, Saturn, and Uranus. Neptune remains the missing piece among the giant planets until Webb's near-infrared sensitivity finally provides the needed clarity. The mid-latitude position of the light then becomes more than a visual curiosity. It becomes direct confirmation that Neptune's strange magnetic arrangement is not an abstract property, measured only by instruments in passing. It actively controls where atmospheric energy appears as visible structure on the planet today. There is also a difference in mood between these auroras and the more familiar auroral scenes of Earth. The Neptune glow is not described as a bright crown encircling a pole, or as a large curtain draped across a dark sky. It is detected in infrared observations and rendered in the combined image as localized cyan patches on the disk. The effect is quieter and more elusive than the ordinary human image of aurora. This is partly because of distance and instrumentation, and partly because the physical arrangement itself differs. Neptune's auroras belong to a cold, hydrogen-rich upper atmosphere under very weak sunlight, at a world whose magnetic poles are not close companions of its rotational poles. The result is a pattern that seems displaced, almost sideways, when judged against terrestrial expectation. That sideways placement is exactly what makes the discovery so informative. It shows that Neptune's auroras are native to Neptune's own geometry, not pale copies of the light seen nearer the Sun. The mid-latitude placement also helps explain why Neptune has been such a difficult auroral target. A polar search pattern informed by other planets might not match the real distribution of light at Neptune, and the light itself is faint in the visible sense, and best revealed through Webb's near-infrared capability. NASA explicitly states that actually imaging the auroral activity on Neptune becomes possible only with Webb's near-infrared sensitivity. When that instrument finally opens the correct observing window, the auroral zones appear not in the simplest expected places, but in the displaced regions demanded by the planet's field. In this way, the discovery joins two kinds of precision. One is technological, the ability to detect subtle remote emission from a dark distant world. The other is planetary, the fact that Neptune's own magnetic arrangement places the signal where only a Neptune-specific search can fully make sense of it. Seen in this outer to inner path, the auroral zones mark the first place where Neptune's invisible magnetism becomes a pattern of light upon the planet. The solar wind remains outside at first, then enters the magnetic domain, and now, at these middle latitudes, the path of energy becomes visible in the upper atmosphere. Observations indicate that the auroral emissions detected by Webb are distinctly southern in the infrared data set reported in Nature, while NASA's image-based explanation emphasizes the broader mid-latitude placement as the key contrast with Earth, Jupiter, and Saturn. These two descriptions are consistent rather than conflicting. One highlights the direct observed emissions in the data set, while the other explains the larger geometric truth that Neptune's auroral activity is displaced away from the rotational poles. It remains uncertain how the full auroral pattern varies across time and longitude, because the present observations capture particular viewing conditions rather than an endless continuous record. But what is already known is sufficient to change the picture of Neptune. Its auroral sky is no longer hypothetical, and it is no longer polar in the simple terrestrial sense. So the discovery settles into place with a kind of calm precision. Neptune, far from the Sun and long difficult to read, now shows direct auroral light. That light appears where the planet's strange magnetic field leads it, not where ordinary expectation would place it. The mid-latitude zones become the first clear atmospheric signature of the leaning, offset magnetic geometry measured decades earlier by Voyager 2 and now made visible by Webb. In those displaced patches of glow, the planet's hidden field writes its shape across the upper sky. What Webb finds next is not simply a patch of light on Neptune, but a spectral signature, a fingerprint in infrared light that reveals what kind of excited material is present in the planet's upper atmosphere. NASA states that, in addition to the image itself, Webb obtains a spectrum of Neptune in June of the year 2023 using the near-infrared spectrograph. A spectrum is light spread into its component wavelengths so that each wavelength can be measured separately. Different atoms, ions, and molecules absorb and emit at particular wavelengths, allowing a distant world to be tested by light alone. In Neptune's case, Webb detects an extremely prominent emission line signifying the presence of the trihydrogen cation, written as H3+, and NASA identifies this ion as something that can be created in auroras. The discovery therefore rests not only on seeing where the glow appears on the planet, but on recognizing the specific signal carried by that glow. The trihydrogen cation is a positively charged form of hydrogen produced under energetic conditions. In giant planet atmospheres, it is especially useful because it acts as a tracer of auroral activity. NASA's Webb release notes that H3+ has long been a clear signifier of auroras on Jupiter, Saturn, and Uranus, and that astronomers expect the same indicator at Neptune once observations become sensitive enough. That history matters. It means the Neptune detection does not stand alone as an isolated curiosity. It belongs to a well-established pattern of hydrogen ion physics at the giant planets. Yet Neptune remains the last of the major giant planets to yield this signal directly, which gives the new observation a special weight. The line does not merely add detail. It changes Neptune's auroras from long suspected to directly confirmed. An emission line has a simple meaning. Excited matter does not shine equally at all wavelengths. It radiates more strongly at particular wavelengths characteristic of its state. A strong line in a planetary spectrum therefore means that one species stands out clearly against the wider atmospheric background. NASA describes Neptune's H3+ line as extremely prominent. This suggests not a marginal hint, but a feature strong enough to support confident interpretation. The auroras become visible in two linked ways at once. In the combined images, they appear as localized patches on the disk. In the spectrum, they appear as a distinctive chemical signature in the light itself. The discovery is therefore both spatial and physical. It shows where the activity is and what kind of ion is helping produce the infrared glow. This result is especially valuable because Neptune is distant, cold, and faint. Image alone can be difficult to interpret when a target is remote and atmospheric signals are subtle. A spectrum provides discipline. It allows scientists to say not only that Neptune brightens in certain places, but that the brightening includes the signature of H3+. NASA's official summary states that imaging Neptune's auroral activity is only possible with Webb's near-infrared sensitivity, and the same observing campaign with the near-infrared spectrograph is used to characterize the composition and measure the temperature of the planet's upper atmosphere. The image and the spectrum therefore support one another. One reveals the position of the glow, while the other reveals the identity of a key ion within it. H3+ also has a practical importance in hydrogen-rich atmospheres because it shines in the infrared and can be associated with energetic electron impacts on molecular hydrogen. NASA's official Webb material on Neptune and Jupiter describes it this way: linking the ion to auroral processes and to strong infrared emission. Neptune's atmosphere is mostly hydrogen and helium, with a smaller amount of methane. So the broad chemical setting needed for this kind of ion exists in the upper atmosphere. When auroral particles enter that region, conditions can produce H3+, and that ion can then radiate at wavelengths Webb is well equipped to detect. The resulting line is not simply a feature on a graph. It is the measurable sign that incoming particle energy is being translated into a specific atmospheric response. Before Webb, Neptune remains difficult in exactly this spectral way. NASA notes that astronomers have seen tantalizing hints of auroral activity in the Voyager 2 flyby and continue to investigate the planet with leading ground-based facilities, yet imaging and confirming the auroras still evade them. The challenge is not only the great distance, it is also the weakness of the signal and the need to separate a genuine auroral spectral feature from the broader faint light of the planet. H3+ is useful precisely because it offers a distinct target in the infrared. Once Webb has the needed sensitivity, the signal does not have to be guessed from indirect traces alone. It can be recognized as a line with its own strength and identity. That shift from hint to direct spectral detection is one of the most important parts of the new Neptune result. There is a quiet elegance in the fact that such an important discovery turns on invisible light. Neptune remains a dark blue world in weak sunlight, and the decisive evidence does not arrive as a bright visible curtain. It arrives as infrared structure gathered from far away and separated into fine spectral detail. Light leaves Neptune, crosses the enormous distance to Earth, enters Webb, and is sorted into wavelengths. Out of that patient process comes the finding that H3+ is present and prominent. Observations indicate the signal is clear. It remains uncertain how its strength changes over time and across all regions of the planet, because the present data represent particular observations rather than an endless continuous record. But the result now stands. In the spectrum of Neptune, a hidden hydrogen ion emerges clearly enough to make the auroral glow chemically legible and directly real. Above Neptune's visible cloud tops, above the pale hazes and the brightest high clouds, there's a thinner and more rarefied region where sunlight, charged particles, and atmospheric chemistry meet. This is the ionosphere, the upper atmospheric layer in which some atoms and molecules have been ionized, meaning they have lost or gained electrons and therefore carry electric charge. On a giant planet, this region is not a separate hard shell. It is a broad high-altitude zone where the atmosphere becomes electrically active, and where magnetic and particle effects can leave measurable signatures in the light. NASA's Webb announcement states directly that the observations taken in June of the year 2023 include a spectrum used to characterize the composition and measure the temperature of Neptune's upper atmosphere, identified there as the ionosphere. That detail gives the new Neptune discovery a wider significance than the auroras alone. Webb does not merely reveal a long-sought glow. It opens the ionosphere of Neptune to direct modern study in a way that earlier observations do not fully achieve. The result is a new observational window into the highest atmospheric layer that still belongs clearly to the planet itself. This upper region is physically delicate. Neptune's atmosphere is mostly hydrogen and helium, with methane providing part of the chemistry that shapes the planet's visible color. But in the ionosphere, the main scientific interest shifts away from the broad blue appearance of the world and toward charged particles, infrared emission, and the response of rarefied gas to energy deposited from above. The air there is extremely thin compared with the deeper atmosphere below. Sunlight is weak at Neptune's great distance, yet it still participates in ionization and heating. Energetic particles guided by the planet's magnetic field can also enter this region and alter its chemistry. That is why the ionosphere matters so much to the auroral discovery. Auroras do not simply hover above a planet in abstract space. They are the visible or infrared result of energetic particles interacting with the upper atmosphere, and on Neptune the upper atmosphere now studied by Webb is specifically the ionosphere. In this layer, the planet's magnetic geometry, the arriving particle energy, and the atmospheric composition finally meet in a form that can be measured by spectroscopy. For many years, Neptune's ionosphere remains difficult to observe clearly. The planet is far away, faint and cold. Its upper atmospheric signals are subtle, and the tools available before Webb do not provide the same combination of sensitivity and near-infrared capability needed to isolate the auroral and ionospheric signatures with confidence. NASA notes that astronomers see hints of auroral activity in the Voyager 2 era and continue to study Neptune with major ground-based facilities, but direct imaging and confirmation of the auroras evade them until Webb. The ionosphere is part of the reason. It is a high, thin, and elusive layer, not bright in the simple visible sense, and not easy to separate from the rest of the planet's already faint emission. Webb changes this by allowing the upper atmosphere to be studied through the specific infrared light of the trihydrogen cation, or H3+, and through measurements of the thermal state of the region. The discovery therefore transforms the ionosphere from a mostly inferred or weakly constrained layer into one with direct modern observational footing. The importance of H3+ in this region is especially quiet and elegant. In a hydrogen-rich upper atmosphere, this ion can form under energetic conditions and radiate strongly in the infrared. NASA's Webb release explains that H3+ has long been a clear signifier of auroral activity at Jupiter, Saturn, and Uranus, and that the same signal is finally found at Neptune, in the ionosphere. This means the atmosphere is not merely present as thin gas. It is chemically and electrically responsive. The upper layer receives energy, changes state, and emits characteristic light. That light is then captured by Webb and turned into a spectrum from which scientists can infer composition and temperature. The ionosphere thus becomes legible not by direct touch, as in a spacecraft plunge, but by remote sensing from far across the solar system. A faint infrared line carries the news that the uppermost atmosphere is charged, active, and connected to Neptune's magnetic environment in the way scientists long expect, but only now directly confirm. There is also a wider scientific meaning in the phrase new window, which NASA uses in describing the discovery as a totally new window in ice, giant atmospheric science. A window in this sense is not a single fact, but a newly opened way of observing a class of processes that were previously hidden or only partially accessible. Neptune and Uranus are both ice giants. Yet Neptune has remained the missing piece in the direct auroral record of the giant planets. Now that the ionosphere can be examined through Webb's near-infrared view, it becomes possible to compare Neptune more directly with the other giant planets and to ask how an ice giant's magnetic field, upper chemistry, and thermal state work together. The ionosphere is especially valuable because it sits at a boundary region within the planet it belongs to the atmosphere, yet it is strongly shaped by magnetospheric forcing and external particle input. It records both the planet's own structure and the influence of the surrounding space environment. That makes it a natural meeting place for several branches of planetary science at once. Even so, much remains uncertain. The Webb result shows that Neptune's ionosphere can now be studied directly, but it does not mean that every property of that region is already mapped in full detail. Observations indicate the presence of a strong H3+ signal and allow measurement of the top atmosphere's temperature. But the full variability of the ionosphere across time, latitude, and longitude is not yet completely known. Neptune rotates, Its magnetic field is strongly tilted, and space weather from the Sun changes through time, so the upper atmosphere is likely not static in its detailed behaviour. Careful science therefore keeps the balance clear. What is known is that the ionosphere has now been open to direct modern investigation through Webb sensitivity and spectroscopy. What remains uncertain is the full pattern of how this high layer changes and couples to the magnetosphere over longer spans. The discovery is therefore both a confirmation and a beginning. In this newly opened ionosphere, Neptune becomes more than a blue planet with distant weather. The world reveals an upper atmospheric layer that is thin, charged, and responsive to energy arriving from above. It is here that the auroral signal becomes chemically specific, thermally measurable, and scientifically rich. The magnetosphere guides particles downward, but the ionosphere is where that guidance is recorded in the state of the atmosphere itself. Webb's observations do not merely brighten Neptune with a new patch of light. They give access to the high atmospheric frontier where the planet meets electricity, chemistry, and infrared radiation in one quiet but decisive discovery. At the top of Neptune's atmosphere, the new Webb result reveals something as important as the auroras themselves, and in some ways even more surprising. The upper atmosphere is much colder than scientists expect from the earlier Voyager 2 era. NASA states that the Webb observations allow the temperature of the top of Neptune's atmosphere to be measured for the first time since the flyby in the year 1989, and the result shows this high region has cooled by several hundreds of degrees. The same NASA report says that the temperature in the year 2023 is just over half of what it is in the Voyager era. This is a large change, and it reshapes the meaning of the new auroral discovery. Before the Webb observations, astronomers often estimate how bright Neptune's aurora should be by using the older upper atmosphere temperature. If the top of the atmosphere is now far colder than assumed, then the expected infrared auroral signal would be much fainter as well. In that quiet way, a thermal result helps explain an observational puzzle that lasts for decades. Neptune may not have lacked auroras in the modern era. It may simply have had auroras too faint to be clearly detected until a telescope with enough sensitivity and the right infrared reach finally observes them directly. This cooling belongs specifically to the upper atmosphere, not to the whole planet in a simple general sense. The distinction matters. Neptune remains an internally active world with strong winds and long-lived weather systems, and that broader atmospheric vigour is not erased by a colder top layer. What Webb measures is the thermal state of the highest atmospheric region accessible through the new spectrum, the region associated with the ionosphere and with the newly confirmed auroral signal. Temperature in such a high layer does not behave exactly like temperature at the visible cloud tops or deeper down where weather bands and major storms live. At great altitude, the gas is very thin. Energy can arrive from sunlight, from charged particles, and from atmospheric motions rising upward from below, while energy can also be lost through radiation into space. The measured temperature therefore records a balance among several processes, rather than only the amount of sunlight reaching Neptune. This is one reason the result feels so important. Neptune is more than 30 times farther from the Sun than Earth is, and yet this remote upper region still changes enough over the decades to alter whether its auroras can be seen. A colder upper atmosphere means fainter auroral emission, because the infrared glow scientists use to trace auroras depends strongly on the thermal and chemical state of that rarefied gas. NASA explains the point plainly. Astronomers predict the intensity of Neptune's auroras using the temperature recorded by Voyager 2, and a substantially colder temperature would lead to much fainter auroras. The Webb result therefore provides not just a new number, but a new reason for an old absence. Neptune has long been the missing giant planet in the direct auroral record. Jupiter, Saturn, and Uranus all yield clearer auroral detections earlier. Neptune does not. After Webb, the absence no longer seems like a simple failure of expectation. It begins to look like a consequence of real atmospheric change. The upper atmosphere may have cooled enough that the familiar auroral indicator, though still present, drops below what earlier instruments can comfortably isolate. The discovery is calm in tone but strong in implication. A remote world once thought merely difficult to observe turns out to have changed in a way that makes the target itself dimmer. This also tells something deeper about Neptune as a climate system in the broad planetary sense. The dramatic cooling suggests that the top of the atmosphere can vary substantially across timescales of decades, even though the planet is far from the Sun and receives weak sunlight. That may sound unexpected at first, because great distance is often associated with stability and stillness. Yet distance alone does not guarantee thermal sameness over time. Neptune rotates. Seasons progress slowly across its long year. Solar activity changes through the solar cycle, and energy can move upward from lower atmospheric layers in ways that are not yet fully constrained. Webb now shows that the top atmosphere is not fixed at the same state seen during the Voyager flyby. Observations indicate that it has changed greatly. It remains uncertain exactly which combination of long-term seasonal effects, solar forcing, atmospheric circulation, and ionospheric processes is responsible for the full cooling, because the new discovery reports the change more clearly than it resolves every cause. That uncertainty is not a weakness of the result. It is part of what makes the result valuable. The upper atmosphere is now known to be more variable than a simple static picture allows. The cooling also changes the emotional scale of the planet in a quiet way. Neptune often appears in imagination as a distant blue world whose main mystery lies in its remoteness. Webb reveals a different kind of mystery. The planet is remote, but it is not thermally frozen in one unchanged state at all heights and times. Its upper atmosphere evolves enough that a key observational signature can fade for decades, and then reappear when a better instrument finally measures both the glow and the temperature controlling that glow. The discovery, therefore, does not simply add a new fact to Neptune. It revises the recent history of what astronomers think they should have been seeing all along. In this highest measurable layer, cold becomes explanation. The newly found auroras are not only faint lights in a hydrogen-rich atmosphere, they are lights shaped by a top atmosphere that is far colder than expected from older measurements. Neptune's upper sky has changed since Voyager 2. The modern value is just over half the earlier one. The cooling amounts to several hundreds of degrees, and the effect is enough to help explain why the planet's auroras remain hidden for so long. At the top of Neptune, the new discovery is therefore not merely that light is present, but that cold has been quietly suppressing that light for years, turning a difficult detection into a finely solvable one. Below the newly measured ionosphere, yet still high above the deeper weather layers of the planet, Neptune presents a quieter visible face made of hazes and bright cloud features. These are the highest atmospheric structures that can be followed in reflected sunlight and near-infrared imaging without dropping into the denser, heavier parts of the atmosphere below. A haze is a broad, suspended layer of very small particles that softens and modifies the light passing through it. A cloud, by contrast, is a more concentrated visible feature formed where material condenses into brighter patches or streaks. On Neptune, these two kinds of upper structure share the same lofty region but do not look the same. The haze gives the planet part of its diffuse atmospheric veil, while the brightest clouds stand out as pale marks against the darker blue body of the world. NASA's Neptune climate reports and image summaries repeatedly describe high-altitude bright clouds and a haze layer as major visible parts of the planet's upper atmosphere. And Webb's close-up view also highlights methane ice clouds on the disk. These upper layers matter because Neptune is not a smooth blue sphere when observed carefully. In ordinary broad impressions, the planet can seem uniform from a great distance, especially in visible light. Yet detailed observations from Voyager, Hubble, ground-based telescopes, and now Webb show that the atmosphere near the top is textured. NASA's historical and recent descriptions note bright linear clouds, bright spots, and changing cloud cover across the disk. The upper haze also influences how sharply such features stand out. A thicker haze can whiten and soften a planet's appearance, while a thinner haze allows the deeper blue color to remain stronger. New research discussed by NASA explains that both Uranus and Neptune possess haze layers. But Neptune's haze layer appears thinner than Uranus's because Neptune's more active atmosphere is better at cycling methane particles through the haze and removing some of them again. This does not make Neptune haze-free. It means the planet's high haze is present but comparatively less dominant, allowing the world's stronger blue appearance to remain visible. The bright clouds in this upper region are especially striking because they do not share the deep blue tone of the surrounding atmosphere. NASA's Hubble material explains why these high clouds can appear white or pale rather than blue. They form above most of the methane in Neptune's atmosphere and therefore reflect sunlight more broadly instead of being strongly shaped by the same methane absorption that gives the planet its blue color overall. This makes the high clouds stand out as bright features against the darker disk. Voyager 2 sees linear bright clouds high in Neptune's atmosphere, and later Hubble observations continue to show high-altitude clouds in both hemispheres. In some images they appear almost cirrus-like in their brightness and delicacy, though the comparison is only visual and does not imply an Earth-like sky. The important point is that Neptune's upper atmosphere is layered enough that its brightest clouds sit above much of the absorbing gas below, and can therefore reflect light in a cleaner, paler way. This high visible weather is also changeable. NASA's long-term Hubble report on Neptune's disappearing clouds shows that the amount of cloud cover in the upper atmosphere has waxed and waned over years, with an intriguing correspondence to the solar cycle and with a pronounced drop in recent years except for some clouds near the South Pole. The report describes how cloud activity fades rapidly beginning around the year 2019 and remains low in later observations. That finding belongs specifically to the cloud cover visible at high levels of the atmosphere. It means that the upper visible layer is not static, not permanent in one fixed pattern, and not simply a decorative skin over a deeper unchanging world. It evolves over time. Some years show more bright cloud structures across the disk. Other years show much less. The upper atmosphere of Neptune is therefore not only lofty and thin, it is observably variable. This variability gives the recent Webb auroral work an additional visual context. The auroral detection is made in the upper atmosphere, but Neptune's disk is already a place where faint and bright high features compete for attention. A world with upper haze, bright reflective clouds, and changing local contrast is not easy to interpret from far away. The highest visible atmospheric region is layered in both a physical and observational sense. Some structures are broad and diffuse, like haze. Some are compact and bright, like discrete clouds. Some vary across months or years. Some may be linked to broader atmospheric circulation, while others respond more strongly to external forcing or local uplift. The present section stays with appearance rather than deeper mechanism, but appearance alone is enough to show why Neptune is not visually simple at high altitude. Even before one descends into the chemistry or the more forceful weather bands below, the upper atmosphere already has texture, brightness contrasts, and change over time. Webb's modern close-up of Neptune reinforces this impression. NASA's summary of Webb Solar System images states that the Neptune close-up highlights the planet's dim rings, methane ice clouds, and several of its moons. In the image description, the bright patches of clouds are especially noticeable against the disk. This does not replace the long Hubble record, but it adds a new kind of clarity to the upper visible atmosphere. Webb sees Neptune in infrared wavelengths that make certain high features stand out strongly. Earlier, Hubble and Voyager views already established that high bright clouds are real and recurrent. Webb adds a cleaner and sharper modern look at how such lofty cloud structures punctuate the upper atmosphere. Together, these observations show that the top visible region of Neptune is not a broad, smooth wash, but a layered field of haze and elevated cloud formed under very weak sunlight. There is also a subtle relation between haze and brightness. NASA's explanation of the color difference between Uranus and Neptune notes that Neptune's atmosphere may be more effective at stirring methane particles into the haze layer and producing methane snow, which helps keep the haze thinner than Uranus's. Even without dwelling yet on the deeper chemistry behind that process, the visible consequence is useful here. A thinner haze allows Neptune's stronger blue to remain more vivid, while bright upper clouds can still stand out sharply where condensation has formed lofted reflective structures. The upper atmosphere therefore presents two intertwined visual facts, at once a planet-wide veil that affects the overall softness and color of the disk, and localized pale cloud features that mark places where the highest visible weather gathers into brighter forms. In this upper visible region, Neptune reveals a calm but changing face. The haze softens the atmosphere without hiding it completely. The bright cloud tops punctuate the disk like high, pale islands suspended over darker blue depths. Long observation shows that these features come and go, sometimes fading greatly, sometimes returning in greater abundance, always reminding observers that even the highest visible atmospheric layer of this distant ice giant remains alive with motion and change. Before any descent into the deeper chemistry and stronger circulation below, the upper hazes and bright clouds already show Neptune as a world whose remote beauty is made not of uniform blue alone, but of a thin atmospheric veil and a changing scatter of high reflective weather. Neptune's blue appearance begins with a simple fact of composition. The planet's atmosphere is made mostly of hydrogen and helium, with a smaller amount of methane mixed through the accessible upper layers. NASA's current Neptune facts page states this directly and explains that methane absorbs other colors of sunlight while allowing blue light to be reflected, giving Neptune and Uranus their similar basic hue. That description is scientifically modest, but it is the foundation of the planet's visible identity. Neptune is not blue because its atmosphere is made of blue material. It is blue because methane changes the balance of light that escapes back to space. Redder wavelengths are more strongly absorbed, while shorter wavelengths are left to dominate the reflected view. In that quiet filtering of sunlight, a distant ice giant becomes the deep blue world seen through telescopes and spacecraft cameras. This process takes place in a hydrogen-rich atmosphere that would not, by itself, produce Neptune's familiar color. Hydrogen and helium are the main constituents. But methane plays the more visually decisive role because even a relatively small amount can affect the spectrum of reflected light strongly. NASA's Neptune poster and facts resources describe this in nearly identical terms. Methane absorbs red wavelengths and allows blue ones to be reflected back into space. The effect is not a painted surface or a fixed outer skin, It is an atmospheric filtering process. Sunlight enters the upper atmosphere, interacts with gas and suspended particles, and emerges altered. The planet's colour therefore belongs to the behaviour of light within a layered atmosphere rather than to the colour of a solid ground below. Neptune has no solid surface visible in the ordinary planetary sense, only progressively deeper atmospheric layers merging downward into hotter and denser material. The blue world is an effect of air, light, and chemistry. Yet methane alone does not fully explain why Neptune appears more vivid than Uranus. NASA's Webb planning material for the ice giants and its later science explainer on their colour difference both make this point clearly. Methane gives both planets their basic blue or blue-green appearance, but Neptune's blue is more striking. The more recent NASA explanation says that Neptune's atmosphere is more efficient at churning methane particles up into the haze layer and producing methane snow, which removes more haze and leaves Neptune with a thinner haze layer than Uranus. With less haze to soften or whiten the view, Neptune's blue looks stronger. This is an important refinement. The old simple statement that methane makes Neptune blue remains true, but the deeper modern picture adds the role of haze structure and atmospheric activity. The planet's colour is not set by methane alone. It is also shaped by how the atmosphere handles particles, haze, and condensation at different heights. That makes Neptune's visible colour a product of layered atmospheric balance. Methane absorbs red and infrared light, but haze can dilute or modify the resulting appearance. NASA's explanation of the Uranus-Neptune colour difference describes a three-layer aerosol structure in the broader ice giant atmosphere and argues that Neptune's more active atmosphere helps keep the middle haze layer thinner by converting methane particles into snow that falls deeper. The present section remains at the level of visible upper atmospheric chemistry, so the key point is straightforward. Neptune looks more strongly blue not only because methane is present, but because the atmospheric veil above and within the methane-rich region is thinner than on Uranus. The blue therefore emerges more cleanly. In planetary appearance, transparency matters almost as much as composition. The same gas can produce somewhat different worlds when the haze above it is handled differently by atmospheric motion. The role of methane also helps explain why high clouds on Neptune can appear pale or bright against the darker blue body of the planet. NASA's image resources and climate summaries note that high clouds stand above much of the methane that colours the atmosphere below. Because they sit at greater altitude, they can reflect sunlight before it passes as deeply through methane-rich layers, and so they are not shaped in the same way by the red light absorption that gives the planet its broader blue appearance. The result is a useful contrast. The deep atmosphere reads as blue because methane filters the light, while the high clouds can appear white or pale because they reflect more broadly from above much of that filtering path. This gives Neptune's disk its visual complexity blue background, bright cloud tops, and subtle haze all working together in one atmospheric view. Methane is also central to Webb's modern images of Neptune. NASA's explainer on exploring the solar system with Webb states that the close-up view of Neptune highlights methane ice clouds. In infrared observations, methane-related absorption patterns can make some atmospheric features stand out differently than they do in visible light. This matters for the recent auroral work because Neptune's upper atmospheric behaviour is being studied through infrared sensitivity, not only through ordinary visible appearance. Methane therefore belongs to two connected stories at once. It helps shape the familiar blue face of the planet in reflected sunlight, and it also influences how deeper and higher features separate from one another in infrared observations. The chemistry that colours Neptune is not only decorative, it helps determine how the atmosphere can be read scientifically across wavelengths. The presence of methane further reminds the mind that Neptune's atmosphere is chemically simple in its main ingredients, but visually rich in consequence. Hydrogen and helium dominate by amount, yet methane, though smaller in abundance, has outsized importance for what observers actually see. NASA's educational and science pages repeat this because it remains the clearest bridge between chemistry and appearance. A slight constituent changes the planetary colour. A thinner or thicker haze modifies that colour further. High clouds interrupt it with brightness. Infrared views reveal still more structure. Neptune thus becomes a lesson in how minor atmospheric ingredients can govern the visible identity of a major planet. What looks like a single deep blue globe from afar is, in reality, the product of wavelength-dependent absorption and layered scattering in a cold, distant atmosphere. There is still some uncertainty in the full story. NASA's Webb preparation page says that some still mysterious atmospheric chemistry likely contributes to Neptune's especially vivid blue compared with Uranus, while the later NASA explanation offers a strong haze-based mechanism tied to atmospheric turbulence and methane snow. These are not mutually exclusive statements. Together they show that the broad cause is understood and that some finer details remain active areas of research. Observations indicate that methane is essential, and that haze structure and atmospheric activity help explain the difference in appearance between the two ice giants. It remains uncertain whether every contributing microphysical detail has been fully resolved. Neptune's blue is therefore both explained and still scientifically interesting, which is often how planetary understanding advances. In this chemical layer of the outer atmosphere, Neptune's colour becomes intelligible without losing its quiet beauty. Hydrogen and helium provide the main body of air. Methane filters the sunlight. Haze thickness alters the intensity of the blue. High clouds shine above the absorbing layers. The result is a planet whose appearance is not a simple surface property, but a spectral consequence of her atmospheric composition and structure. What NASA has newly found on Neptune belongs to the auroral and upper atmospheric story. But that story sits upon this older and deeper visual truth. The blue world is blue because methane changes the light, and because the atmosphere above and around that methane allows the change to be seen so clearly from far away. At the top of Neptune's visible weather, the atmosphere gathers into bright cloud structures that stand out with unusual clarity against the darker blue body of the planet. These are the highest cloud tops that can be followed directly in telescopic views, and they have a special visual importance because they sit above much of the methane that darkens and colours the atmosphere below. When sunlight reaches these lofty clouds, it can be reflected before passing deeply through the methane-rich layers beneath, so the clouds do not appear strongly blue like the planet around them. Instead, they appear pale, bright, and sometimes almost white. NASA's long record of Neptune observations describes these features in nearly the same language across decades. Voyager 2 sees linear bright clouds high in the atmosphere. Hubble later records bright clouds thought to be above the main cloud deck and above much of the absorbing methane gas. Webb, observing in the near-infrared, shows them again as bright streaks and spots, especially in the southern hemisphere, where methane ice clouds become some of the most prominent visible atmospheric features on the disk. The continuity across these missions is important. It shows that Neptune's highest clouds are not a brief anomaly of one observing era, but a persistent part of the planet's upper weather, even though their details change over time. These upper cloud tops are generally understood as methane ice clouds. In a cold outer atmosphere where methane is present, the gas can condense at suitable heights and temperatures into ice crystals, producing bright reflective structures high above the darker background atmosphere. NASA's Hubble and Webb image descriptions identify the high clouds on Neptune as methane ice clouds, and the bright appearance follows naturally from their position. Because they are elevated above much of the methane that absorbs red and infrared light, they reflect sunlight more directly back toward the observer. This effect becomes especially striking in infrared observations. NASA's Webb description notes that methane gas makes Neptune itself quite dark at near-infrared wavelengths, except where high-altitude clouds are present. In other words, the upper cloud tops stand out not because they generate their own light, but because they remain visible where the rest of the atmosphere has become strongly dimmed by methane absorption. The cloud tops therefore act like small elevated mirrors in a generally darkened atmospheric field. They are not spread evenly across the planet. They appear as patches, streaks, bands, and discrete bright marks, which gives the upper atmosphere a textured and changing appearance rather than a smooth one. The shapes of these clouds also matter. Voyager. 2 describe some of them as linear, bright clouds high in the atmosphere, and later NASA image archives compare them visually to cirrus clouds on Earth. The comparison is only a visual aid, not a claim that Neptune has Earth-like meteorology, but it helps convey their delicacy and lofted appearance. Some are narrow streaks, some are compact spots, some form broken bands across certain latitudes. Hubble observations from the 1990s show bright cloud bands and discrete bright clouds, while later records show compact methane ice clouds near polar regions and narrow cloud bands at other latitudes. Webb adds a particularly sharp near-infrared view, in which bright patches in the southern hemisphere dominate the upper atmospheric texture. The highest cloud tops are therefore not a single type of structure repeated uniformly across the globe. They are a family of upper atmospheric forms produced at high altitude under local conditions that vary across latitude and time. Their common trait is not shape but elevation. They sit high enough to be seen above most of the methane-darkened atmosphere below. Their brightness is also a clue to height. NASA's older Hubble descriptions explain that the bright cloud features are most obvious in red and infrared wavelengths, where methane gas absorbs strongly. This simple observational fact gives away their vertical placement. A cloud that remains bright where methane below would otherwise darken the atmosphere must be positioned above much of that absorbing gas. The cloud tops therefore reveal something about Neptune's vertical layering without any need to descend yet into deeper atmospheric mechanics. They show that the atmosphere is not one uniform blue volume. It is a stacked structure in which some features ride high enough to escape the optical effects dominating the levels below. This is why the cloud tops appear almost like separate weather marks written onto the face of the planet. They belong to the same atmosphere, but they are optically privileged by altitude. In visible and infrared imaging alike, height becomes brightness. The highest cloud structures are not static. NASA's Voyager record notes that Neptune's bright cirrus-like clouds can change rapidly, often forming and dissipating over periods of several to tens of hours. This is a remarkable statement for a world so distant from the Sun. It means the top visible weather layer can evolve on timescales short enough to matter within a single observing sequence. Hubble later confirms that Neptune's upper cloud cover changes substantially over months and years, while Webb provides a fresh modern snapshot of bright methane ice clouds in a different spectral view. The top clouds therefore combine persistence with restlessness. They are persistent as a class of atmospheric feature across decades of observation, yet individual structures can appear, shift, brighten, and fade on far shorter timescales. This gives Neptune's upper atmosphere a paradoxical calm. The planet looks serene from afar, but its highest visible weather is active enough to redraw itself repeatedly. In this upper cloud-top region, Neptune presents one of the clearest examples of how altitude changes appearance. The deeper atmosphere provides the blue world, the haze softens and veils it, but the highest methane ice clouds interrupt that field with pale brightness, standing above the absorbing layers and catching sunlight cleanly enough to announce their presence across billions of kilometers. Their forms may be narrow, broken, compact, or streaked. Their positions may vary by latitude and epoch. Their lifetimes may range from hours to years, depending on the structure being followed, yet their meaning remains consistent. They are the visible uppermost weather marks of Neptune, bright, because they are high, and high enough to reveal that even the top of this distant atmosphere is never truly still. Across Neptune's visible atmosphere, motion gathers into broad bands, powerful jets, and fast-moving cloud systems that make the planet the windiest world known in the solar system. NASA's current Neptune Facts page states that winds there can exceed 1,200 miles per hour, or about 2,000 kilometers per hour, fast enough to be several times stronger than Jupiter's winds and far stronger than the most powerful winds on Earth. This remains one of the most arresting facts about Neptune because the planet is so distant from the Sun and receives so little solar energy compared with the inner planets. A world that appears calm and dim from afar turns out to host some of the strongest atmospheric motion in the planetary system. The large-scale weather is not random in shape. It organizes itself into bands and zones, visible as subtle belts of changing color and cloud texture across the disk, and these broad patterns provide the stage on which faster local features move. NASA's image archives repeatedly describe Neptune as blue and banded with clouds and storms, and that phrase is accurate in a literal physical sense. The atmosphere is layered into broad latitudinal structure, and those structures are alive with swift motion. The bands are not as sharply contrasted to the eye as the belts of Jupiter, yet they are real and scientifically important. Voyager 2 sees a bright blue planet with distinct atmospheric features distributed by latitude, including the Great Dark Spot, the Lesser Dark Spot, and the fast bright cloud feature called Scooter. Hubble and later observatories continue to record large storms, companion clouds, and changing cloud patterns across specific belts. These repeated observations show that Neptune's atmosphere is not a uniform blue shell. It contains broad regions where flow differs with latitude, where some zones are darker, some brighter, and some more favorable to the formation of visible high clouds. NASA's older Hubble color descriptions note a powerful equatorial jet centered on a dark blue belt just south of the equator and identify belts farther south, where the atmosphere interacts with light differently. Even where the bands are visually subtle, they remain dynamically meaningful. They mark a circulation pattern in which neighboring latitudes can move at different speeds and in different ways, giving Neptune a structured atmospheric rhythm rather than one single global flow. These winds are extraordinary not only in speed but in persistence. NASA's Neptune Facts page emphasizes that frozen methane clouds are whipped across the planet by these winds, and the phrasing is exact in spirit. The atmosphere does not merely drift. It moves hard and continuously enough that clouds form, shear apart, and race along latitudinal tracks under extreme conditions of cold and weak sunlight. Voyager 2's direct encounter already reveals that Neptune is more active than many scientists expect before arrival, and NASA's historical summaries still underline that surprise. The planet is not a quiet outer sphere slowly turning in stillness. It is active, stormy, and driven by strong organized flow. The high cloud structures recorded by Voyager can change on timescales of hours, and that rapid visible evolution makes sense only in an atmosphere where winds are not incidental but dominant. The broad bands therefore do more than decorate the disk. They channel some of the fastest air motions known on any planet. One of the best ways to understand these winds is through the dark storms and their companion clouds. NASA's Hubble work on Neptune storms explains that bright white companion clouds form when surrounding flow is disturbed and forced upward over a dark vortex, allowing gases to freeze into methane ice crystals. The storms themselves can last for years, and NASA reports that new major storms may form every 4 to 6 years, with some surviving up to roughly 6 years, though shorter lives may be more common. These long-lived vortices move within the broader banded circulation rather than existing outside it. They are weather systems embedded in the zonal flow, meaning the broad west-east wind pattern arranged by latitude. The cloud bands, bright companions, and dark spots are therefore connected pieces of one atmospheric picture. Neptune's large-scale winds create the framework, and within that framework storms emerge, drift, shrink, and vanish. The visible atmosphere becomes a record of motion written across latitude. The equatorial region gives a particularly useful example of this organized speed. NASA's Hubble color interpretation from the 1990s identifies a powerful equatorial jet where winds blow at nearly 900 miles per hour, centered on a dark blue belt just south of Neptune's equator. Other latitudes support their own patterns and storm activity, showing that Neptune's atmosphere is not driven by one simple global stream. Different belts can host different flow speeds, different cloud behavior, and different kinds of visible structure. This is why the term banded matters. It implies the atmosphere has latitudinal organization, not just scattered storms on an otherwise featureless world. A jet is a fast, narrow current of air, and on Neptune such currents reach strength that would be astonishing anywhere else in the solar system. The darker and brighter bands on the disk are therefore not only optical variations. They are signatures of differing atmospheric regimes, places where velocity, temperature, cloud formation, and vertical motion are not all the same. What makes all this so striking is the planet's energy setting. Neptune is far from the sun, and yet NASA still describes it as dark, cold, and whipped by supersonic winds. The phrase is not just vivid language, it points to a genuine scientific challenge. Solar heating alone seems insufficient to account for the vigor of the weather that is observed. The visible atmosphere behaves as though it has access to more driving energy than distant sunlight would suggest by itself. NASA's fact pages present the observational side. Clearly the winds are real, they are extreme, and the weather is active. The deeper explanation of what sustains that activity belongs farther below, but at the level of the visible bands and winds the central point is already secure. Neptune's atmosphere is dynamically stronger than the simple distance from the sun might lead one to expect. The bands and jets are the observable proof of that strength. The modern picture that emerges from Voyager, Hubble, Webb, and later analysis is therefore one of orderly violence. Neptune's atmosphere is not chaotic in the sense of lacking structure. It is structured strongly enough that bands persist. Jets organize motion by latitude, and recurrent storms follow recognizable patterns. Yet within that structure, wind speeds reach planetary extremes, and visible features can change quickly. Bright methane ice clouds streak across the disk. Dark vortices appear and disappear over years. Companion clouds gather where the flow is pushed upward. Broad belts remain in place long enough to define the face of the planet, while the weather inside them keeps moving. Neptune's upper visible atmosphere is thus both stable in architecture and restless in detail. That combination is one of the reasons the planet remains so compelling. Its distance suggests stillness, but its bands and winds reveal the opposite. The outermost great blue world is not sleeping under the weak sun, it is moving with exceptional force. Beneath Neptune's brightest upper cloud tops lies the deeper troposphere, the lower main weather layer of the atmosphere where pressure rises steadily downward. Gas becomes denser, and the visible simplicity of the blue world gives way to a more crowded and layered meteorology. Neptune does not have a solid surface beneath this region in the ordinary planetary sense. Its atmosphere extends to great depths and gradually merges into hotter, denser fluid material below. That means the troposphere is not a thin shell resting on ground. It is part of a deep atmospheric body, and as one moves downward through it, clouds and hazes do not simply disappear. They change level, composition, and optical effect. The highest bright methane ice clouds belong to the upper troposphere, and recent Neptune studies identify such clouds at pressures of roughly 0.1 to 0.6 bars. Below that level, the atmosphere becomes thicker, darker in a visual sense, and more difficult to read directly because sunlight penetrates differently, and because overlying methane and aerosol layers obscure what lies beneath. Yet observations and models show that the deeper troposphere is not featureless. It contains broad aerosol structures, latitudinal banding, and additional cloud layers whose likely compositions differ from those of the highest clouds seen most clearly from afar. This lower weather region is where the atmosphere starts to feel heavy rather than delicate, and where Neptune's visible face becomes the product of several layers stacked one above another, rather than a single blue envelope. The broad observational picture is now reasonably clear even though many details remain hard to pin down. Methane condenses in the upper troposphere and forms the highest cloud layer. Deeper down, a cloud layer made largely of hydrogen sulfide is widely considered likely, and radio analyses of Neptune's atmosphere have long suggested that hydrogen sulfide is more abundant relative to ammonia than older, simpler expectations assume. Still deeper equilibrium cloud models for Neptune include ammonium hydrosulfide, water ice, and even aqueous ammonia solution droplets at very high pressures, showing that the lower troposphere is chemically stratified rather than uniform. This does not mean each layer is seen directly in the way a mountain cloud deck is seen on Earth. Much of the deeper structure is inferred from spectroscopy, radio observations, and cloud condensation modeling rather than from simple visual imaging. But the layered interpretation is strong enough that Neptune's deeper troposphere can now be described as a place where methane clouds occupy the upper reaches. Darker and deeper aerosol structures shape much of the banding, and heavier sulfur and water-related condensates likely appear farther down as pressure and temperature rise. Recent spatially resolved work on Neptune's atmosphere supports this layered picture by identifying upper tropospheric methane clouds and also linking some prominent banding to deeper aerosol layers visible at wavelengths that probe more deeply into the atmosphere. That is an important observational bridge, because it shows that some of Neptune's visible banded structure is not only a matter of the highest clouds, but of material and contrast rooted farther down in the troposphere. The deeper troposphere is therefore where the planet's weather stops looking like a pattern of isolated bright cloud tops on blue background, and starts becoming a vertical system in which different pressures reveal different kinds of atmospheric structure. Pressure itself is one of the quiet rulers of this region. At the upper levels, clouds can remain thin, bright, and optically privileged because they sit above much of the absorbing methane below. Deeper down, the same atmospheric column becomes more opaque, denser, and less transparent to direct remote viewing. Light that escapes from those levels has passed through more gas and more suspended material, so information from depth becomes harder to separate. This is one reason Neptune's deeper troposphere remains only partly known. Observations indicate strong latitudinal variations in methane abundance and aerosol opacity, and those variations are especially visible at wavelengths that probe deeper than the highest haze layers. Even so, the lower atmosphere is not yet mapped in complete detail across all latitudes and times. Some structures are seen clearly as bands, bright spots, or dark regions, while the exact vertical placement and composition of every aerosol layer remain matters of ongoing refinement. What is already secure is that the troposphere is vertically differentiated, and that the visible atmosphere cannot be understood by looking only at the cloud tops. It is also a region of condensation sequence. In giant planet atmospheres, different substances condense at different pressures and temperatures, and Neptune's deep cold chemistry means methane can already condense high in the troposphere, while sulfur-bearing and water-bearing condensates appear lower down. This layered condensation is not merely chemical bookkeeping. It changes reflectivity, cloud brightness, opacity, and the depth from which radiation can escape. It helps explain why some wavelengths show high bright clouds, some reveal deeper banding, and some point toward lower aerosol layers not obvious in ordinary visible views. The deeper troposphere is therefore the place where Neptune's weather grows more concealed but also more fundamental. Here the atmosphere is thick enough that the visible planet becomes an interpretation of depth rather than a direct view of one single level. The world seen through telescopes is a selective portrait painted by radiation, escaping from particular pressures, not a simple surface image. In Neptune's deeper troposphere, the weather grows heavier, the cloud layers become more varied, and the bands seen across the disk derive more of their character from aerosol structure and vertical composition than from the brightest cloud tops alone. This is still the atmosphere, still the blue world, still the same moving planet, but it is no longer the high, delicate realm of pale methane ice clouds. It is the denser lower weather layer where pressure builds. Sulfur likely becomes more important than ammonia in key cloud-forming regions, and the atmosphere's visible order rests on a deeper and more stratified foundation than the upper sky first suggests. Below Neptune's visible weather, and already felt above it, there is a quieter source of motion heat rising from within the planet itself. NASA's Neptune science pages and Hubble reports make this point plainly. Neptune does not merely reflect and re-radiate the weak sunlight that reaches it from so far away. It gives off more energy than it receives from the sun. That single fact changes the meaning of the atmosphere above. A world so distant from the sun might be expected to show subdued weather driven only by meagre solar input. Yet Neptune does not behave that way. Its winds are extreme, its storms can be large and changing, and its cloud systems remain active across years and decades. The broad scientific picture therefore begins with an energy imbalance. Neptune is not only warmed from outside, it is warmed from below. NASA's more recent materials on the outer planets state this in slightly different forms, but the underlying idea remains the same. A Hubble science page explains that Neptune radiates about 2 times more energy than it receives from the distant dim sun. A recent NASA science article on Uranus, discussing the giant planets more broadly, states that Jupiter, Saturn, and Neptune each emit more energy than they receive from the Sun, which means they have comparatively warm interiors. Older NASA technical literature places Neptune's emitted to received ratio even higher in some analyses. The exact number depends on the model, the wavelengths measured, and the treatment of the energy budget, but the consensus point is stable. Neptune has a substantial internal heat source relative to the sunlight available at its orbit. That is why the planet's weather cannot be understood as sunlight alone acting on a cold static shell. This internal heat matters because atmospheric circulation depends on temperature differences. When one region is warmer than another, energy can move, gases can rise or sink, and large-scale flow can develop. NASA's Hubble material on Neptune's storm says the cloud tops may be warmed from below by this strong internal heat source, and notes that even slight changes in the temperature difference from cloud bottom to top might trigger rapid, large-scale changes in atmospheric circulation. A later Hubble description of Neptune's anniversary portraits makes a similar point, stating that the temperature contrast between the strong internal heat source and the frigid cloud tops may trigger instabilities that drive major weather changes. An instability is a situation in which a fluid state does not remain quiet but begins to overturn, mix, or organize into stronger motion. On Neptune, that means heat from below can become wind, banding, and storm activity above. The importance of this inward warmth becomes especially clear when Neptune is compared with Uranus. NASA's outer planet and instrumentation pages repeatedly note that Uranus lacks significant internal heat, while Neptune does not. The two planets are similar in size and broad class, and both are called ice giants, yet their atmospheres do not behave alike. Neptune is more dynamic, shows stronger storms, more vigorous vertical activity, and a more active visible atmosphere. NASA's description of the difference is direct. Uranus lacks internal heat, while Neptune radiates as much energy as it receives from the Sun, and this internal energy gives Neptune an active, dynamic atmosphere marked by dark belts, bright methane ice clouds, and cyclonic storms. Even if the exact heat ratio is phrased somewhat differently across different NASA pages, the physical contrast is clear. Neptune is the more internally energized of the two, and its weather reflects that distinction. This does not mean sunlight is irrelevant at Neptune. Solar energy still reaches the planet, still interacts with methane, haze, and the highest clouds, and still contributes to the upper atmospheric state. Seasonal changes are also real. Hubble observations of Neptune across decades show that cloud activity shifts with time, and NASA has linked some visible cloud changes to the solar cycle and to the slow march of the planet's long seasons. But the broader atmospheric vigor cannot be attributed to sunlight alone. Neptune's orbit is too distant and the sunlight there too weak for solar forcing by itself to explain the observed strength of the winds and the persistence of major weather systems. The atmosphere is therefore best understood as being driven by a combination of outside influence and inside energy, with the internal heat source carrying far more importance than distance from the Sun might first suggest. The precise origin of that internal heat is not fully settled in one simple sentence, and careful science leaves that point open. NASA and related planetary literature generally treat Neptune's excess energy as part of the planet's retained internal warmth and deep energy transport, a remnant of formation and subsequent internal evolution that continues to leak outward over time. Broader giant planet studies also frame the problem as one of how the interior and atmosphere transport heat to space. Observations indicate that Neptune's internal energy output is real and comparatively strong among the giant planets. It remains uncertain exactly how the planet stores, releases, and channels that heat through all depths and timescales, or why Neptune's ratio of emitted to received energy is so large. This uncertainty does not weaken the main result. It simply means that the fact of excess heat is better established than every detail of the process carrying it upward. What can already be said with confidence is that this inward heat changes the whole character of Neptune's weather. A warmer lower atmosphere beneath far colder cloud tops creates the possibility of convection, which is the rising of warmer material and the sinking of cooler material. In a giant planet atmosphere, convection need not appear as one simple continuous overturning everywhere at once. It can occur in patches, interact with latent heat from condensing substances, and feed into larger jets and vortices. NASA technical discussions of Neptune's atmosphere point to major unknowns in convection, latent heat release, and the interaction with the fluid interior. But they also make clear that internal energy is central to the problem. Neptune's fast winds and organized storms are therefore not just surface appearances. They are the atmospheric expression of energy moving upward from below and then being redistributed by the rotating planet. This helps explain why Neptune can be both frigid and active at the same time. The cloud tops are extremely cold, and the planet receives little solar energy. Yet the atmosphere does not settle into passivity. Instead, it supports powerful jets, bright high clouds, changing dark spots, and strong vertical motions. The contradiction softens once the internal heat source is taken seriously. The upper atmosphere may be cold, but it sits above a reservoir of inward warmth that keeps the larger system from becoming meteorologically still. NASA's Neptune Facts page, Hubble storm reports, and long-running atmospheric observations all point in the same direction. Distance from the Sun does not make Neptune inert because the planet is not living on sunlight alone. Its weather is partly fed by energy generated or retained within the planet itself, and then carried upward into the atmospheric layers that telescopes can see. In this deeper atmospheric layer, before the eye has yet reached the planet's hidden interior, Neptune's discovery story becomes one of energy balance. The upper atmosphere glows faintly with newly detected auroral light. The high clouds drift and reform. The bands and storms race through a world of weak sun and strong wind. Under all of that lies a steady physical truth. Neptune is warm from within, in a way that matters to the atmosphere above. It radiates more energy than it receives. Its cloud tops sit over a strong internal heat source, and that contrast helps sustain the motion that has puzzled and attracted observers for decades. The blue world is not driven by faint sunlight alone. Its weather rises, in part, from hidden warmth below the visible sky. Deeper than Neptune's visible weather and deeper than the pressure levels that telescopes can probe with confidence, the planet passes into a hidden interior region that planetary scientists often describe as a mantle of hot, dense fluid. NASA's Neptune Facts page states that most of the planet's mass, 80% or more, is made of hot, dense fluid composed of icy materials such as water, methane, and ammonia lying above a small rocky core. In planetary science, the word icy does not mean this deep region is made of ordinary cold ice blocks like those found in a freezer or on a winter lake. It refers instead to substances that are called ices because of their chemistry, and because they would commonly be frozen at much lower temperatures and pressures. Inside Neptune, those same substances exist under crushing pressure and intense heat, in forms very different from familiar surface ice. The planet's deep interior is therefore not a simple stack of gas over solid ground. It is a world of dense fluid material, gradually reached by descending through thicker and hotter atmospheric layers until the atmosphere merges into melted and altered ices below. This inward region matters because it is the place where Neptune becomes an ice giant in the full physical sense. The hydrogen and helium that dominate the upper atmosphere do not make up most of the total mass. The larger share belongs to the deeper hot fluid interior, where water, methane, and ammonia-bearing material are thought to occupy a vast fraction of the planet. NASA's description is cautious but clear on this point, and it adds that scientists think there may even be an ocean of superhot water under Neptune's cold clouds. held in place not by coolness, but by enormous pressure. Pressure in this context means the force exerted by overlying material. As one descends into Neptune, more and more atmosphere and fluid lie above, so the pressure rises to values far beyond anything on Earth's surface. Under such conditions, matter can remain fluid even at temperatures that would normally drive rapid boiling at low pressure. Neptune's deep interior is therefore not best imagined as one tidy ocean with a familiar surface. It is a realm of compressed fluid phases, where the old distinction between atmosphere, ocean, and icy mantle becomes blurred. This is also the region most closely linked to Neptune's magnetic field. NASA's mission concept work for a future Neptune orbiter explains that gravity and magnetometer measurements would be used to determine the location and nature of the magnetic field generating dynamo. A dynamo is the process by which motion inside electrically conducting fluid generates a magnetic field. The same mission concept paper states that Neptune's magnetic fields are likely generated in a relatively shallow ionic fluid region. Ionic here means a fluid in which charged particles can move and conduct electricity. That detail is important because it helps explain why Neptune's magnetic field is so unlike the simpler centered dipole that might be expected from a deep central metallic core. If the magnetic field is being produced in a shallower electrically conducting shell within the hot fluid mantle, then the resulting field can naturally become more irregular, more offset, and more strongly tilted relative to the planet's rotation axis. The strange outer magnetic geometry seen by Voyager and reflected in the newly detected auroral placement above Neptune may therefore be rooted in this deep but not fully central conducting layer. That possibility gives the mantle region a special scientific importance. The field measured around Neptune does not look like a simple magnetic pattern generated in the most central and symmetrical way possible. NASA's facts page says the main axis of Neptune's magnetic field is tipped over by about 47 degrees, compared with the planet's rotation axis, and mission concept work notes significant tilt, offset, and non-dipolar structure. The interior explanation most widely discussed is therefore not one of neat central symmetry, but one of fluid motion in a shell that is both electrically active and relatively shallow compared with the total size of the planet. Observations indicate that a convection-driven dynamo is widely agreed upon as the source of the field, while the same research summary also states that the deeper reason the field is so non-dipolar and non-axis symmetric remains poorly understood. In other words, the broad mechanism is accepted, but the detailed geometry is still an active problem. The hidden mantle is no longer merely a reservoir of compressed exotic fluid. It is the likely workshop in which Neptune's magnetic identity is forged. The word convection is useful here. Convection means movement driven by differences in temperature and density, in which warmer material tends to rise and cooler material tends to sink. In a dense conducting fluid, such motion can help generate and maintain magnetic fields. NASA's mission concept material treats Neptune's internal heat release, atmospheric convection, and dynamo characterization as connected problems rather than separate ones. This makes sense because a planet's energy flux and its fluid motions belong to one larger system. Heat moving outward can stir material. Stirred conducting material can help generate a magnetic field. That magnetic field then shapes the magnetosphere and eventually influences where auroral particles enter the upper atmosphere. At Neptune, the outer discovery of auroras and the deep hidden dynamo are therefore linked across a great vertical chain. The light found high above the cloud tops may trace its ultimate geometric cause to fluid motions far below them. Yet this deep region remains only partly known. No spacecraft has entered Neptune's mantle. No instrument has watched its internal flows directly. Scientists infer its nature from gravity, magnetic data, atmospheric composition, heat flow, and theoretical studies of matter under extreme pressure. NASA's Neptune facts page gives the broad structural picture with confidence: hot, dense fluid of water, methane, and ammonia above a small rocky core. Beyond that, important uncertainties remain. Mission concept literature says that determining the location and convective dynamics of the dynamo requires future investigation, and it describes Neptune's dynamo and interior structure as central unanswered questions. Observations indicate the magnetic field is real, tilted, offset, and unusually complex. It remains uncertain exactly how the conducting region is arranged, how deep the zonal winds extend, and how strongly the atmospheric circulation interacts with the dynamo below. The mantle region is therefore both partly mapped in broad terms and still hidden in its most important details. The picture that emerges is one of depth without direct sight. The upper atmosphere of Neptune can be imaged. The auroral glow can now be detected. The high clouds can be tracked, and the winds can be measured. But the magnetic field that helps guide the auroras likely owes its existence to this deeper fluid interior, where pressure transforms common molecules into dense electrically active matter. Here, Neptune is no longer blue in any visible sense. Colour has lost its role. Chemistry remains, but under such intense conditions that chemistry becomes part of planetary architecture rather than appearance. Water, methane, and ammonia are no longer the simple atmospheric trace gases and condensates known higher up. They are part of a vast compressed interior mass whose motions may be responsible for one of the most unusual magnetic fields in the solar system. In this mantle and dynamo region, Neptune becomes most deeply itself. The world's outward appearance, its upper weather, its auroral glow, and its magnetic asymmetry all point inward toward a hidden shell of hot, dense fluid under enormous pressure. NASA's current broad description and mission planning studies agree on the essential structure. Most of Neptune is made of this dense ice giant material, and the magnetic field is likely generated within a relatively shallow conducting fluid region inside it. The exact motions, shapes, and boundaries of that dynamo layer remain uncertain, but the broad connection is already strong. Deep within Neptune, long below the clouds and below the levels where sunlight still matters, a restless fluid interior likely shapes the tilted magnetic field that later writes itself into the planet's auroral sky. At the deepest level that current science can meaningfully describe, Neptune appears to contain a small rocky core wrapped in an enormous surrounding mass of hot, dense fluid. NASA's Neptune facts page states that most of the planet's mass is made of hot, dense fluid materials above a small rocky core, and this simple description remains the broad consensus view. The word small is relative to the size of the whole planet, not to human scales. Neptune is a giant world, and even a comparatively small central rocky core would still be massive by any ordinary standard. Yet the important point is structural proportion. The core is not the planet in the way Earth's rocky body largely is. It is the innermost nucleus inside a much larger fluid-dominated world. Everything above it, from the conducting mantle that likely helps generate the magnetic field to the deep troposphere, high haze, ionosphere, and newly detected auroral glow, depends in one way or another on the planet's internal organization. The core is therefore less important for what it looks like, which remains inaccessible, than for what it anchors. It is the deepest inward limit of the known structure, the place where description becomes spare and uncertainty grows strongest. Science. NASA.gov. This deepest region cannot be seen directly. No spacecraft has entered Neptune's interior, No probe has sampled the core, and no telescope can look through the planet's vast depth as if through clear water. Knowledge of the core comes instead from the combined logic of planetary mass, size, gravity, atmospheric composition, magnetic behavior, and models of how giant planets form and evolve. Neptune's measured mass and radius show that it cannot be made only of hydrogen and helium in the same proportions as Jupiter and Saturn. Its density is too high for that. At the same time, the atmosphere does contain hydrogen and helium, so the planet cannot be purely rocky either. The result is the now familiar ice giant picture: an outer atmosphere rich in hydrogen and helium, a vast interior dominated by compressed water, methane and ammonia-bearing material, and a rocky innermost center. This broad model is strong enough to guide scientific work and mission planning, yet it does not dissolve all uncertainty. The exact size, composition, state, and boundary structure of the core remain incompletely known. Science, NASA, Gov. That uncertainty matters because the recent auroral discovery does not only add a feature to the sky above Neptune, it casts new light on the whole chain from the upper atmosphere downward. NASA's Webb report describes the first clear direct capture of Neptune's auroras, and also emphasizes the unusual magnetic geometry that helps place them away from the familiar polar pattern seen on other worlds. Once that magnetic geometry is taken seriously, the inward questions become unavoidable. If the field is tilted, offset, and complex, what arrangement of conducting material inside Neptune produces it? If the upper atmosphere has cooled strongly since the Voyager era, how does energy move upward from the deeper planet through the atmospheric column? If the planet emits more energy than it receives from the Sun, how is that energy stored and transported through the interior? The auroral discovery therefore works like an opening rather than an ending. It confirms something at the top of the atmosphere, but in doing so it sharpens attention on the regions below that still cannot be observed directly. The deepest interior becomes more scientifically alive precisely because the newest discovery occurs so far above it. Science, NASA, Gov. The rocky core itself is likely under conditions far beyond direct earthly experience. Pressure there would be immense, temperatures extremely high, and the material state unlike the ordinary rock familiar at the surface of terrestrial planets. In giant planet interiors, even the phrase rocky core is partly a simplifying label. It suggests a concentration of heavier elements in the center, rather than a calm, solid globe with a neat, sharp surface. Depending on temperature, pressure, and composition, the transition from the overlying dense fluid mantle to the innermost core may not be as clean and simple as early textbook pictures imply. Some models allow for gradients rather than crisp boundaries, and the exact mixtures of silicates, metals, and other heavy materials remain uncertain. What is known is that Neptune must possess a deep central concentration of heavy matter to match its bulk properties, and that this central region sits beneath the vast mantle that dominates the planet's mass, and likely plays the major role in generating the magnetic field above. Science, NASA, Gov. This is also where the outer to inner journey through Neptune reaches its most honest limit. The upper atmosphere can now be observed directly by Webb in ways that were not possible before. The auroras can be identified, their mid-latitude placement recognized, the trihydrogen cation signal measured, and the temperature of the ionosphere compared with older Voyager data. The high clouds and visible weather can be imaged repeatedly across decades. The broad atmospheric composition can be constrained. The excess internal heat can be inferred from the energy budget. The tilted magnetic field can be measured from spacecraft data and linked to a likely shallow dynamo region. but the core remains a place of inference. It is the deepest region where broad structure is accepted while many particulars remain hidden. In that sense, Neptune's newest discovery does not finish the story of the planet. It makes the unfinished parts more vivid. The better the upper atmosphere is understood, the more valuable the unseen interior becomes as the remaining source of explanation, science, NASA, Gov. So the inward descent ends not with a final solved object, but with a quiet boundary of knowledge. Neptune appears to have a small rocky core, and above it a planet-sized mass of hot dense fluid, internal heat, atmospheric motion, and magnetic complexity. That much is well grounded. It remains uncertain exactly how the deep interior is arranged, how sharply one layer gives way to another, how the core and mantle interact across time, and why Neptune's magnetic field takes the precise asymmetric form that it does. What NASA has just found on Neptune is therefore both concrete and suggestive. The auroras are real. The upper atmosphere is colder than expected. The ionosphere has opened to direct modern study. But the deepest reason the planet is the way it is still lies far below, in a hidden interior whose broad outlines are known and whose finer truths remain out of reach. Neptune keeps its center in darkness, and that darkness is now more scientifically meaningful than before. Neptune settles again into distance. The newly found auroral light remains faint. The upper atmosphere remains colder than earlier decades suggest, and the blue planet continues to turn under weak sunlight at the far edge of the major planetary system. What is known now feels clearer than before. Energetic particles from the sun still reach the planet. The magnetic field still guides them in an unusual geometry. The upper atmosphere responds with a glow that had long been expected and only now is directly seen. A hidden layer has opened, and a distant world has become slightly less silent. Yet Neptune also keeps much of itself concealed. The bright cloud tops drift above darker depths. The fast winds cross a frigid sky. Heat still rises from within, feeding motion on a planet that receives little warmth from the sun. Far below, the dense fluid interior likely shapes the strange magnetic field that later writes itself into the auroral zones high above. Deeper still, the core remains inferred rather than seen, present through gravity, structure, and mass, but still hidden from direct view. So the discovery rests in a calm balance between knowledge and distance. It does not turn Neptune into a solved world. It makes the world more legible while leaving its deepest workings largely intact as mystery. A faint light in the upper sky becomes a guide to magnetic shape, atmospheric state, and internal structure. One new observation reaches downward through many layers of a giant planet and ties them together more tightly than before. In that way, Neptune remains true to its nature. It is remote, blue, cold, and active. It reveals itself slowly. Even now, after the auroras are finally seen, the planet still keeps its center beyond direct sight and its full story unfinished. The farthest great blue world continues to move in darkness, carrying both fresh discovery and older silence together.